Today we are going to do section 5.5 on page 471, the zeros of polynomial functions. Now I have to say that finding zeros of polynomial functions have never been my favorite cup of tea when it comes to algebra or math in general, but even if you find it a bit tedious, it's very tedious to me. It doesn't mean that math overall is going to be as tedious as this. It's just that every hobby, everything you love to do, you know, there's almost always tedious parts to it. Like I see people waiting in line overnight for, I don't know, the new iPad or something like that. It just it's just the way it is. Okay, sometimes that happens. We just push through it, and then the better lives are coming. There's a lot more fun to life, to math, that is, than finding zeros. But we just have to grind through it if you find it tedious. If you don't find it tedious, if you find it exciting, that's even better. Okay, never mind what I just said. Forget I said anything about it being tedious. It's not. But anyway, so having said that, let's get going. First, let's look at the middle of the page where we're talking about the remainder theorem. What that means is that, let's say you have a polynomial, okay, and then we divide it by long division. We divide it, and then it becomes a quotient, and then you will have some kind of a remainder. Now, if you do that, then your polynomial will look something like this. Okay, now if you plug x equal to k in this equation, so now it becomes f of k, then you have k minus k in this part, right? And which means that will become 0, so f of k is going to be whatever's left, that remainder part. And so as a result, the remainder based on this information can be calculated. If you divide f of x by something such as x minus k, where k is some number, then the remainder simply by plugging k into f, and then doing the math, and that will give you the remainder. Right? And that is the entire part of the remainder theorem, which says that if a polynomial f of x is divided by x minus k, and k can be either positive or negative, doesn't matter, then the remainder is when you plug k into f and see what comes out. Okay, it's the value f of k. Now, having said that, then let's look at example 1. We need to figure out what is the remainder at x equal to 2. Okay, so then let's plug x equal to 2 in this thing. Let me write it down. So what happens is that, let's say we have a function f of x, is this big long thing, and we want to divide this thing by that, and what we want to know, what is the remainder? Okay, what is the remainder, question mark, if we're dividing by x minus 2, and the rule says the remainder is simply f of 2. So let's calculate what that is. Well, let's plug 2 in there, okay? So that will be 6 times 2 to the power 4 minus 2 to the power 3 minus 15 times 2 to the power 2 plus 2 times 2, and then minus 7. Yeah, so at this point, let's do it. Okay, that's 6 times 2 to 6 times 16, right? That's a 6. Minus 8 minus 15 times 4 is 60, and then plus 4. 2 times 2 is 4, and then minus 7. Yeah, let's pull out the calculator and see what this says. All right, so I pushed it all into my calculator, as you can see here. That should be able to zoom in okay this way. All right, so let's see what my calculator says, assuming I didn't type in anything wrong. So it says the remainder is 25. So let's check our answer to see if I got it right. Yep, it is correct. So the remainder of f of x divided by x minus 2 would be 25, and we do it by using the remainder theorem by plugging 2, whatever you're subtracting, plugging that thing in here, and that will give you the answer. And that's by using the remainder theorem. Yeah. Anyway, so next, let's look at the next thing, the factor theorem. Now, the factor theorem on the following page is I'm on page 472, which says that the polynomial has a 0 equal to k if x minus k is a factor of the polynomial. Okay, it's similar to that is, in other words, if x minus k factors, that means its remainder is 0. Okay, that's where the logic comes from. So having said that, then in other words, if the remainder is 0, then this is the x minus whatever becomes a factor of the polynomial. So let's do an example, see what that means or how that works out. And let's look at example 2 at the bottom of the page. I'll write it down. All right, so here's example 2, which I forgot to write down. Okay, now the example 2, we're giving a polynomial and we need to show that this thing is a factor. And we're gonna do that by showing that so this x plus 2 is the same as x minus negative 2, okay? We have to show that this number, whereas in the x minus k form, okay, the k is minus 2. We need to plug in f of k. F is this thing. F is the polynomial. We have to show that f of k, we're going to show that f of k equals to equal to 0. If that is the case, then this x plus 2 is a factor. In this case, k equals to minus 2. So what is f of minus 2? Well, we're just going to plug it in and see what it says. F of minus 2, so that becomes to the third power, that is negative 8. Okay, f minus 2 equal to minus 8. And then minus 6 times squared becomes positive 4. And then minus 2, and then plus 30. All right, yeah, so I'm gonna try to do this in my head and see if I can be lucky and not mess up. So this is minus 8 minus 24 plus 4 plus 30. That is 28 plus 24, that's 30. So that should be 4. Now, you can do it in your head or you with a calculator, your choice. Okay, it doesn't make much difference. All right, so why should it be 4? Well, I'm obviously wrong because it's supposed to be a factor, right? Let me see. Did I get the polynomial wrong? No? So then I must have done this math wrong. Where did I get wrong? Let's see. Minus 2 to the third power is, let me figure out where I got wrong. All right, now I found my mistake. First, this is not plus 4. This is plus 2. Why did I say 4? I have no idea, which means this is wrong. All right. So this is plus 2, okay? And that is 0, for heaven's sake. Yeah, that's, what is that? And that is minus 8 minus 24 is minus 32. And then plus 32 is 0. All right. And then, so next, let's, therefore, this is a 0. Now that we know that it is a 0, the next thing we need to do is we have to factor factor this whole thing, okay? Which is a bit of work, but we're just gonna have to do it. Now, x squared, I don't think the normal factoring is going to work, okay? It doesn't, the quick, easy factoring. We're going to have to do long division, which I don't like, but there is no getting out of it, okay? It's tedious. So let's do long division. The book does synthetic division, which is a bit faster because you don't have to write down all the x's. But I like to write down all the x's. That way I feel that it's slightly less likely for me to mess up. Well, let me write this out better. So anyway, we are going to do long division in order to find the rest of the factors. We don't. You might wonder how often in algebra do we have to do this, finding zeros or any factoring polynomials. I would say not often. Okay, and if it was often, I would have taught you how to do synthetic division. But I rarely, if ever, touch it in any classes in algebra or beyond after we finish this section. So anyway, but for now, since we're in this section, let's do it. Okay. so this time let's do long division, which we did in the previous section, and let's do this again. Let's see, so that's x squared, right? So the x squared be x cubed plus 2x squared, and then do the subtraction. 6x squared, and then minus x, write that thing down, that will be minus 6x to become x squared. Okay, so that becomes minus 6x squared, and then minus 12x. And this thing had better come out with remainder to be 0. If it isn't, that means there is a big problem. I think I'm already seeing a big problem. Let me check. All right, I already found the big problem. Let's get rid of that. It's minus 6 minus 2. Okay, that should be minus 8. All right, try again. So this is a minus 8. Okay, and then let's get rid of this. Okay, this is times this has need to be that. So minus 8. That's much better. So minus 8 x squared. And then minus 8 times 2 is minus 16x. Okay, and then do subtraction again. The subtractive becomes 15x minus 30. And then to get there, then we have plus 15 times. So that's 15x minus plus 30. Wait a second. Did I get this right? Let me check again. No, sorry. This is, let me check again. Okay, I found my mistake. It's a plus 30. Okay, I got this thing wrong. That's why it's not working out. So let's fix that. This is a plus 30. And then that's 15 plus 30. Okay, that looks much better. So that will subtract to be 0. As expected, it better be 0. And because we already proved that it is a factor. Okay, so the remainder had better be 0. So here is the second part of this. So the polynomial f of x then equal to, so f of x equal to x plus 2 times this stuff right here. Okay, and then let's see if we can just factor this. This is just a quadratic, so it tends to be easier. So if we're lucky, we might be able to factor it like this and don't have to do the quadratic formula. But it can be done if you have to. Okay, so 15 we'll do 3 times 5, because 3 times 5 will add up to be 8 somehow. And so here's the x. And then 3 times 5 is 15. It has to be positive, but it has to add up to be negative. So let's do 2 negatives, which will be positive. And then it will become minus 3 minus 5 becomes minus 8. So that is the whole factoring of the polynomial. And next, we need to figure out what does this say. Factoring, find the zeros. Okay, so the question is, what are the zeros? The zeros are all the numbers that make this thing equal to 0. That is, the answer will be, the zeros will be when this is 0, which is the zeros are minus 2. And the next one, when this is 0, which means x equal to positive 3. And then when this is 0, which means x equal to positive 5. So the answer, if I ask you what are the zeros, the exact answer will be minus 2, 3, and 5. Anyway, so that should be good. And so we're done with there's example 2. So let's move on to example 3. And let me erase the board. Let's see, let me move over so you can see it, and then I'll erase it. So next, let's go to page 473 and consider the rational zero theorem at the bottom of the page. The rational zero theorem states that if you have a polynomial and you're looking for the zeros, right, and then every rational zero, that is the zero that is come in the form of a fraction, is going to have the form of a p over q, where p is some kind of a factor of the last term, and q is some factor of the first coefficient. In other words, that let's say you have a polynomial that looks something like that, and then every single zero will be you'll be able to calculate it as it will end up being something that's a factor of a0, the last number, divided by a factor of an, the first number. So to see what that means, let's try an example on the next page, example 3. So let me write that down. So example 3, okay, we have some kind of polynomial here, and then we need to figure out what are the possible zeros. That means that it might be a 0, but it might not be, okay? But we're going to write down all the possible zeros, the rational ones, that is ones that in a fraction form that we can think of. So it says that it will be the factor of this thing divided by the factor of this thing. And what are the factors of this thing? The factors of 4, of course, is including the negative ones. The factors of 4 is would be 1, 2, and 4, right? That's about it. And also the negative versions, -1, -2, -4. And then the factors of 2 will be 1, 2, right? And then also the negative ones, -1 and -2. So all combinations of pick anything out of this list divided by anything out of this list are the possible factors, which sounds like a lot, and it is. But some of them are repeats, so then we don't end up with quite as many. So let's see what that means. Okay, so we'll start here. Okay, that would be 1 over 1 is 1. 1, and then 1 over minus, and then also all the minuses are repeated, so we'll just do it like this to save a little energy. So this just means we have 2 of them, okay, the positive version and the negative version. So we have that, and then next we have 1 over 2. Actually, yeah, no, I think I'm okay. So there's 1 over 2, okay, and then of course also the -1. And then 1 over -1, we included that right here. And 1 over -2 already included. So generally speaking, we don't have to worry about the minus ones because we already said plus or minus. And then remember what the plus minus sign means. It means the positive one and the negative one. We're just playing it lazy and not have to write it twice. So we write it one time like that. So this is actually 2 numbers in here, positive 1, negative 1. And that's 2 things, 1/2 and negative 1/2. So anyway, so let's continue. Next, we'll start here. 2 over 1 is 2, okay? And then we'll just always write down the plus minus 1. And then 2 over 2 is 1, which already did, is right here. So we don't have to write that. And then 2 over -1, we already did that. 2 over -2, we already did that. That's plus or minus 1. So next, we'll consider 4. 4 over 1, that's 4. We haven't considered it, so we'll do it that here. We'll just write down, each one has 2 of them, the positive and negative one, so we might as well write it down. And then 4 over 2 is 2, but we already got 2 down here. And then the negative ones, we already did that. So the total number of positive ones is there are 8 possibilities. Now there are not 8 roots in here. These are just possible ones. Okay, and yeah. So and that's all we need to look for here is all the possible ones. So here's the answer for example 3. That looks a little bit tedious, but in a way it's very, very cool because you look at this thing and you think, what are the possible rational roots? And it looks hard, and how are you supposed to figure that out? And yet the theorem then has reduced the number of options right here. This is all possible roots, which means if you plug in each one in here, okay, and don't mess up in the calculations, then you can check if each number is the correct, it is a real root. And then you would have run, and once you do it 8 times, there are 8 options here, then you would have found all the rational roots. Yeah, I mean, otherwise you're staring at this like, how am I supposed to do this, right? I mean, this theorem enables you to do it. It takes a bit of time and very exhausting to me, but it can be done, and it's not too impossible. Okay, it's exhausting, but not totally impossible. It can be done in a reasonably short amount of time. Depends on how fast you can evaluate all 8 things. So that is, so as a result, it's still a pretty cool theorem because this only depends on the first and the last number. It doesn't matter what's in here. And there can be all kinds of stuff in here. And this still works. So that's what's so neat about it. All right. So next, so this time we just found the possibilities. The next one, we're going to actually figure out what it is. Okay, not just find possibilities, then we'll check our possibilities to see if it actually works. Now let me write down the next example, example 4. So example 4, we have a polynomial here, and we're going to find the rational roots with this trick that we just figured out. Okay. Now, so the trick says that we need to take what's the factors in the end and divide the factor in the very first thing. So what are the factors? So the end factor is plus or minus 1. Okay, and which is good. There's only one thing. And the beginning factors are plus or minus 1. And plus or minus 2. So then when you take this divided by that, we will have the options, our possibilities will be the first one divided by that will be plus or minus 1. And then this divided by that will be plus or minus 1/2. So, and that's, I think that's about it, right? You see anything else? I think those are all the possible roots. So we have 4 options, which is not, so we need to plug all 4 numbers, which is positive 1, negative 1, positive 1/2, negative 1/2 in this thing, and not mess up, and then see if it equals to 0. Because if it equals to 0, then it is a factor. Okay, so let's consider f of positive 1. Start with the easy one, and I don't think 2 plus 3, yeah, I think it's going to work. Okay, that would be 2 plus 1 is 3, minus 4 plus 1, that is equal to 0. So f of 1 equal to 0. So that will work. And now that we know that will work, then we're going to attack it right there and not go any farther. Because, and let's do, so at this point, let's do long division. So let me copy this down, because what this means is x minus 1 is a factor. Okay, so x minus 1 is a factor. Now but before we do long division, let's see if we can get away with factoring, just direct factoring. I don't think so. Yeah, unfortunate. So we have to do long division again. All right, so let's do that. Let me write this down. So I have the polynomial written down. Let's do long division. So something multiplied by x need to be 2x cubed. So that would be 2x squared, right? 2x squared times x will be 2x cubed. All right. And then minus times that will be minus 2x squared. And let's see if I can do a long division without messing up. Ugh. So let's do the subtraction. That should be 3x squared minus 4x. Okay. And then, so something multiplied by x need to be 3x squared. So that will make it positive 3x. And before I go any further, I decided I will check myself, see if I got it right. Actually, the book has no intention of doing that. They are just gonna plug everything in, which is, I guess that might be okay, but I think I'll finish my long division. Okay, yeah. So then let's keep going. So that would be 3x squared. And then minus 3x. That would be equal to minus x, right? Plus 1. That's the very last one. You drop that down. And then this something times x has to be minus x. So that would be minus 1. Times x is negative x. And then that would be plus 1. So as we expected, and the remainder is 0. But we already know the remainder is going to be 0. I was looking for this thing, okay? Because we started out with a third power, and then we reduced it to this, this is a quadratic function, which is much easier to factor most of the time. Let's see if we can, we should be able to do this. So this part equal to, let's do that trick. So we have 2, so the x has to be 2x and x. Okay, we have to make it becomes plus 3 and minus 1. That's if it works. So we'll have plus 1, and then it might not work. Let me see. Minus 1 plus 2. Oh no. Let me check this. All right, this does not factor. Okay, this is not going to work. See, you know why? Because this has there's no factoring of this thing, which means there is no real solution for this. So as a result, f of 1 is the only real solution there is, and so that's it. Okay, that's the only rational solution is f of 1. Because if there was another one, this thing would have factored out. Now the book, of course, checked all the other numbers. Instead of doing this, the book checked all the other numbers. We checked 1. The book also checked minus 1 plus 1/2 and minus 1/2, which, and there's nothing wrong with doing that. That is fine too. Either method shows that this has only one rational root, and that is 1. This of course has complex roots, that is imaginary roots, things that have eyes in it, and the imaginary value. We will look at that in a little bit. So for this, for example 4, then the only rational root we can find is 1. Yeah. Okay. So next, we will continue with example 5 in the next video.